thank you very much. First of all, would like to thank again Joel, Avishai, all this Santa Cruz gang for having me here again. It's really wonderful summers I spent here, and I always carry back plenty of ideas when I go back home. So thank you very much. I hope I'll be able to come in the next years too. So I'm going to talk today about comparing simulations and observations with deep learning. I know it's Friday, and you're all tired because of the long and interesting workshop. So I will simplify a little bit the title of my talk by saying, does a neural network know about horses if it has only seen cats and dogs? And this is, I think, an important question to ask when you try to apply machine learning to science. Now, at this stage, when I talk about neural networks, there's a typical bimodality in the population in this audience, so which is kind of correlated with age, but not always. That says young people are, wow, this is interesting, machine learning, and others say, another black box magic talk. I don't understand anything. So I'll try to guide through you through this idea. And some of you know that we have been running this summer. Now it's still, we have 1 week left. An exciting program in which Brandt is part of the organizing committee and director of the program, a Kavli summer program on machine learning in astrophysics. And we had some wonderful students who have been working for 5 weeks on specific projects. And I thought that I will take the opportunity to advertise or to show some of the work we have been doing during these weeks, especially by 2 students from Southampton and YIU, and who have been working in specific projects on machine learning, so that to show you what we can achieve only on 5 weeks of work. So this is not even preliminary. This is preliminary square, as you can imagine, because it's just the work of a few weeks. But I think it's interesting, and you can have. I'd be happy to have some feedback. Okay, so I think it has become clear during these talks that as simulations observation become more and more big and complex, we have many more simulations, more predictions. We have complex data, low and high redshift. It becomes obvious after listening at all these talks that we need tools of meaningful ways of comparing both to see if we are doing well in the simulations and if we are reproducing the observables and we can trust the predictions that we have. So since the last years, I've been pushing for doing some kind of apples-to-apples comparison through forward modeling. I think it's a good approach to compare simulations observation in the same plane. And this comes from forward modeling, and we have seen already some talks during the week, forward modeling the simulations into an observer's plane, and then use these mock observations to really compare apples to apples in the same plane. And I think at this stage, machine learning is very useful to link those, especially since you can go from you can track in the mock observations what the formation history of these galaxies and try, since these techniques are very powerful in finding features, patterns in the data, you can ask to find physical patterns in this data. And this is something that we have done in the past, especially what is interesting here is that you can try to train based on the physics that you know here and try to test if you see these traces of physics in the observations. So this is something that we did last year, especially with Joel and Avishai, and we've showed, as Avishai showed you yesterday, that we were able to trace or to find a characteristic mass for compaction or blue nuggets based only on the definition, the simulation, but in the candles fields. So, however, all this technique assumes that when you do these mock observations here, these guys live in the same regime, okay? And we know, because otherwise we will be out of job, that simulations are not perfect. And there are things here that are not well reproduced. So if you train on something which is in this space and try to find it here, you are forcing the machine to find it, but maybe it's not there. And so this goes back to the question, what happens if these are horses, and I'm training on horses, but I'm trying to find cats, okay? And this creates an issue when you try to train with things. So we have been thinking with Lorenzo in a way of trying to assess this bias. And if you think about what does it mean that observations match simulations? And if you put it in a Bayesian framework, this means that imagine you have a data set or a survey, I put as an example SDSS, and what you want to have is the likelihood that a simulated galaxy, X whatever, from the given distribution is equal or similar to the likelihood of an observed galaxy given the properties of that survey. And then if you can measure this likelihood and these are more or less equal, this means that both x and xs come more or less from the same distribution. Now, this is a multidimensional space because x can be all the observables that are contained in a given data set. And so what we do typically, and we have seen during the week, is that we reduce the space and we compute the likelihood of sizes in one dimension and compare to the likelihood of sizes in the other space, or 2 dimensions, but we barely go beyond 3. So we look at scaling relations and so on and try to compare that both matches here, okay? So we have thought that we could do something more general and completely fully data-driven. And this is the idea that we had in mind. So we can take, to compute this likelihood, you can take an SDSS galaxy and say, what is the data? What is all the information is there in one? And so this is an image. You can apply multi-wavelength, but which all the information is contained in the pixels, okay? So all the information that you can have is in these pixels, and there's no more information than that. Now you need to extract it and compute the likelihood from that. So you can assume that you can model all the pixel distribution, assuming that every value in a pixel can be reproduced by a probability density function. So you don't know, but every pixel has a probability density function that you can estimate and know more or less with characteristic of Sloan galaxies at a given depth. And if you compute these PDFs for all the pixels in the image, then you will have your likelihood, which is the likelihood of all pixels given an observation or a survey, right? Now, these are, again, multidimensional, but you can simplify this expression by using the chain rule of probabilities. And instead of estimating the joint probability here, you can express or compute the probability of one pixel given the other pixels, conditional probabilities. And then you end up that your likelihood is the product of all the conditional probabilities, okay? And this is a way to estimate the likelihood of all images in Sloan, and you can use a neural network to do that, okay? And this is called a kind of models which are called autoregressive image generation. And this is one example of these are called pixel CNNs, and they try exactly to do that, right? To describe in a probabilistic way, to compute the likelihood of a given data set pixel by pixel. So we tried this game with Sloan galaxies during this summer school. So we took an SDSS data set of about 100,000 galaxies. We run all these images to this pixel CNN, and we learn this likelihood, okay? So we have a model that has learned the likelihood of how Sloan galaxies look like. This is one band, but you can do it in multi-band. And this is what more or less the network has learned. So these are original SDSS galaxies. These are reconstructions that the model does. So it learns how to reconstruct galaxies based on the probabilities. And these are the residuals where you subtract those and those ones. So the model converges to generate and to create SDSS galaxies. So it learns the probability distribution of the pixels in the Sloan. And since it's a probabilistic model, you can sample from this model. Now you can generate new Sloan galaxies as you like, fake galaxies, but following the same likelihood. These are fake SDSS galaxies generated by pixel CNN just by sampling the PDFs, okay? So you see, it's not perfect, but it's, for a human eye, it would be hard to distinguish these from real ones, okay? But these are completely sampled from the model by going pixel by pixel, and you sample a point from the distributions. Okay, so now you have this likelihood model, and you can plot the distribution of all likelihoods in the SDSS. So now you compute the likelihood of all Sloan galaxies. Since you have trained with Sloan, this would be the best case scenario. Okay, see, this is the maximum likelihood that you can get from what the model has learned. So this scale here is arbitrary. It's not important. But basically it's showing you that if you compute the likelihood in a train or a test set, it's more or less similar. So it's not overfitting, and you have some scatter here in the likelihood of Sloan galaxies, which we are investigating what's the reason of this scatter, but still a work in progress. Now we know, you can ask what makes an SDSS galaxy more likely for the model, and these are 2D projection of this 9 or 8 3 by 4, 12-dimensional space with typical measurements of morphology to see if a particular family of galaxies is more likely for the model. That one is colored by the likelihood. So you see that the likelihood is more or less uniform. And you see, for example, if you look at the morphology, that here is a population of late-type systems, another population of late-type systems. Early types more or less like here, but you see no trend with the likelihood, okay? You see no trend also, so massive galaxies are more or less there on the corner, but the likelihood is also constant. So the network more or less has learned all galaxies equally, okay? It knows that all galaxies are equally likely. It has learned properly the SDSS behavior. So now you can play the game and say, okay, now I'm going to do a supervised comparison with simulations to see if they live in the same plane, if they have the same likelihood, if the model knows that I'm now starting showing horses to the model. So I've trained that with cats, and now I'm showing horses. So we have played this exercise with two simulations, Illustris and TNG, and we selected objects with the same redshift and mass cut, and we create these mock SDSS images. And then we feed them to the pixel CNN train on the SDSS. So that you get the likelihood of Illustris given SDSS in the R band and the likelihood of TNG, okay? And you can compare to the distribution of likelihood of Sloan. There's a caveat here, of course, because this depends on radiative processes. So it's not really the likelihood that you get here. You get the likelihood given also a kind of recipe for radiative processing, okay? But since you do the same for both, and you're looking for relative shifts, you can marginalize on those, okay? So if you do that, this is how it looks like. So this is the yellow is, again, the SDSS likelihood that I showed you before, and this is Illustris, okay? So you see it shifted. It's clearly shifted. So the machine is seeing that Illustris is different. It's not exactly as it was expecting. Objects are less likely, so it's surprised, and there's an overdensity of objects over here. So just in one shot and in one metric, you are able to see if your simulations observations live in the same space. Now, you are wondering what happens with TNG. And, well, basically, the network is able to tell you that this is a horse. Now, if you go to TNG, as we all expected since the talks we have seen before, things improved a lot, okay? And you see now the blue line is TNG that almost perfectly matches at the Sloan resolution the likelihood expected. So this doesn't mean that TNG is perfect. This means that at the Sloan resolution, and what you can do in the air band, again, just one band, it's difficult now to distinguish both. You have only, in terms of likelihood, a small tail over here of slightly over unlikely objects. But at the Sloan resolution, they start to be very close. And this is because, and then also, if you look at them using your human eye, you see it starts to be difficult to distinguish which ones are simulated from TNG and which ones are real observations, okay? I'll give you a hint. These are Illustris, or TNG, sorry, and these are ellipticals from SDSS. And also you see that there's you do more classical scaling relations comparison. You see that the mass size relation in Illustris for early type and late type galaxies is quite well reproduced as compared to what you see in Illustris, as Vicente showed. So basically, the network, the likelihood estimation is measuring that things are improved in Illustris by just one single metric. Now you can see, another interesting thing that you can do with this kind of plot is that you can explore these anomalies over here. You see what happens to these objects. Is there something inherent to these objects? Why are these less likely? And this is, again, under exploration, but these will be the TNG weirdos, right? Ones which the model finds they are unlikely. And it's hard to find a pattern, but are clearly well structured with lots of clamps and so on. And these are less likely to be found in the Sloan. I usually find a pattern here, which is a big bulge over here and some kind of ring of star formation. I don't know if it's exactly the ring that you were predicting, but these are rings over here. And these, unfortunately, are not found in the Sloan, or at least the model says they are less likely. Okay, now a question for you. We can, since typically we model Sloan galaxies with Search-seq fits, you can create mock Search-seq fits of all your galaxies, bulge composition, and ask, is this a good model? Is this likely to be the good representation of the Sloan? So what would be your prediction? Where is the likelihood will go? Any hint? So this was the best surprise for me. Searching models are more likely than, they are clearly not as the Sloan, but they are more likely than normal galaxies. So we are still trying to understand that, but the reason I think it is that searching models, so the model kind of learned that the surface brightness of galaxies needs to increase, and probably it's exhibited in a PDF for each pixel, so probably center this PDF on the average flux that it would expect, that probably corresponds with the searching profile, because it's a good fit. So, but there are some fluctuations in the real data, which are clamps and spiral arms that the model learn. While you fit a searching model, it's always in the peak of the PDF, right? So it's very likely, it becomes very likely. And I think this is the explanation, but we are still exploring that. But in any case, what you need to look here is for shifts in the distribution. So this is telling you that searching fit is probably not a good representation, or at least not as good as TNG, which is a good. Okay, so why is this useful? So I think it's an unsupervised baseline to quantify the match between observations and simulations. It can help quantifying the impact of recipes, for example, feedback on a given set of observables. This is one thing I have in mind. Now, Avishai and colleagues have run a generation 3 and generation 6 of Vela with different feedback recipes, so you can kind of feed the same galaxies, but with this only changing the feedback recipe, and see which one become more likely to match the data, for example. And so there are many applications that I can think about these techniques. And finally, in the last minute, another thing that we are doing with Gait, kind of related to that, and this is fully observational, you can use these kinds of techniques to also find unknown unknowns in the data, right? So you know, only from the observational perspective, we are, as Ben said, facing a revolution in data, and we have huge surveys that we won't be able to look at them, right? And for sure, there will be unknown unknowns there. So, and this is where interesting new science might arise. So you want to find them, and by throwing away everything which is not interesting, or not, which is very likely. And see, this is called anomaly detection, and you can use the similar techniques, but now fully data-driven to find strange objects. We did a simple exercise with Gait, training a kind of generative model on the HSC survey, which is the hypersuprime CAM survey. It's 1,400 degrees square on several bands, and we played the game of training a generative model with all HSC sources, and then learn the normal distribution of HSC, and then trying to find which ones are the less likely, to see if we find some interesting stuff there. This is still going on process. This is what the model has learned. So, and these are the likely objects. You see on the top row is the real, bottom is the reconstruction by the model, the CNNs, and bottom is the residuals. And you see that these are likely objects, normal objects. I can reproduce these objects without any issue. I don't have to look at them. Now, if you look now, and if you can compute a kind of likelihood, in this case it's an anomaly score because it's a different definition, but basically it has this shape for 1 million HSC objects, in which you see most of them there's a peak here, more or less all of them are equally likely, but there's a tail here of objects that I struggle to reconstruct, okay? And then you can look at them. So you are reduced from 1 million objects that could be interesting, you are reduced it to just a tiny fraction, and then you can look at them. And fortunately for now, these are pipeline errors. But it's okay. So we are detecting pipeline errors as the first stage. So these are supposed to be magnitude 20 objects, and you see that there are many blank fields over here. Okay? So these are centering, miscentering issues that you are detecting, and so the network says, oh, I was expecting a galaxy here, but there's nothing. So this is very unlikely. Okay? And then we are now trying to explore if we have some interesting stuff. Okay, we have, for example, you can find more interesting things like these merging galaxies, which are a bit unlikely, which you can see more structure. There's a hole over here. I don't know. We are starting to explore. This is very work in progress. Okay, so I'll stop here. Does a neural network know about horses, if as in cats? I think yes. And this we can exploit this to compare simulation with observation, also to find interesting objects in observations. And I will leave you with my conclusions. Thank you.
Questions?
So I don't know if I understood you correctly, but you can find anomalies if you're training on the data. You find anomalies in the simulations. Or are you
You
finding
can find
anomalies
anomalies in the simulation or in the data
in the
itself.
data itself? But in order to find anomalies in the data, you have to train on the simulations?
No, you train on the data.
You can train on the data as well?
But you look for the tails of the distributions.
Ah, okay.
I mean, if these are, you assume that anomalies are a small fraction of your data set. Otherwise,
I see.
so the model will not learn them properly because they are a small fraction, so they will be very unlikely. And then you can capture them like that. But you train on the whole data without knowing anything, and then you explore the tails of the distribution.
And so are you able also then to find objects in the data that you never produce in the simulations in the same method?
Exactly. Yeah.
Okay, thanks.
More question at the back.
So comparing Illustrious and TNG at redshift 0.05, you found that Illustrious had more horses. It was more dissimilar from SDSS.
Right.
Was there any redshift dependence to how much it changed? If you went,
If you go at different redshifts, you mean?
Yeah.
Yeah, so we haven't done that because we need mock data. So I'm planning to do this for candles, for example, at higher redshift and do the same thing, but I'm waiting more for TNG 50 because I think there you have more resolution issues, so I'm not sure. But it's a good point. Yeah.
Thank you.
More questions? I have one.
Yeah.
Have you tried to do this with deeper surveys, for example, with gamma, that is deeper, so try
yet.
to compare
No.
with the...
I mean, again, this is a 4-week project.
Yeah.
So
Yeah, okay.
yeah. Not that much.
Okay, so let's thank Marc again.
Thank you.